Thank you everyone for coming. We have another guest lecture, and today we have Ranjay Krishna. Ranjay Krishna is an assistant professor at the School of Computer Science and Engineering at the University of Washington, and he co-directs the Raven Lab. He has taught previous iterations of CS231N in 2020 and 2021, and his research lies at the intersection of computer vision, natural language processing, robotics, and human-computer interaction. In today's lecture, he will discuss multimodal foundation models. And Ranjay, the floor is yours.
Thank you. It's great to be back. The first time I ever taught this course here at Stanford, it was 2020. And we had about 3 weeks where we had to take all the material and move it online. Every year after that has been much easier to teach. It's great to be back. So today we're going to talk about multimodal foundation models. So a lot of the lectures in this class so far has really been focused on building individual models for individual tasks. So these usually follow a few steps that you've seen over and over again in lectures. You collect a data set, usually a training set as well as a test set. Then you train a very specialized model for that purpose. So that could be an image classification model or image captioning model, like the ones you've seen in your assignments as well. And then you finally sort of evaluate those models on your test set. Now, what's sort of been different in the field so far in the last couple of years is this sort of shift away from these individual models into building these more foundation models. And the way to sort of think about foundation models is that it really is trying to pre-train models on a wide variety of skills, a wide variety of different tasks, and then later on adapt those things for individual tasks depending on your needs. So, for example, one very common foundation model that you all probably use in some form or the other is GPT. And GPT was trained on a lot of common crawl data from the internet, and then you take that model that you get, and then you fine-tune it for different purposes. So you fine-tune that model for math problems or symbolic reasoning or trivia questions, and all of these are individual tasks that this model can quickly adapt to. Now, what's nice about foundation models is that it allows you to sort of do that update step, that adaptation to new tasks, with very minimal data. Meaning you don't need to collect a large amount of training data. You can usually get away with very, very little. Oftentimes, you can even get away with collecting no training data at all. And so when you think about foundation models, there's many different classes of foundation models that you might care about. In language, you've got Elmo and BERT that really started this entire revolution. And then we now have GPT and T5 and variants of these models. These are things we're not going to talk about in this class, since we're mostly going to be talking about multimodal models. What we will talk about is how do you build these same kind of foundation models for image classification. And we'll go into examples like Clip and Coca today. We'll also talk about how do you combine language models that you might have seen already in class with these sort of vision foundation models to enable all kinds of new models, multimodal foundation models that can solve a wide variety of tasks. And then, of course, we can do a lot more than just sort of solve tasks in language. We'll talk about how you can build models that can output not just text, but also masks, or images that you might want to generate. And then finally, we'll talk about this idea of chaining, where you take a bunch of foundation models and then combine them to do all kinds of new things together. Now, when we talk about foundation models, there's many different ways to classify them. And it's hard because the definition is often sort of disagreed upon. But what you typically will see in a foundation model is that it's robust and general to many different tasks. So you can apply that same model for all different use cases. And I'll show you a ton of use cases today. Also, something else that's common in a lot of these foundation models is that they have a lot of parameters. They have large amounts of parameters, large amounts of training data, and usually they're trained with some sort of self-supervised objective. Okay, so of course, we're not going to talk about the language stuff. What we will talk about are the ones in green today. And so let's get started with image classification. So how do we actually go about building a foundation model that can solve image classification for any sort of data set you might care about? Now, if you remember from a few lectures ago, we were talking about self-supervised learning. And in self-supervised learning, one of those methods that you saw was SimClear, where you have this contrastive objective that contrasts against dissimilar images and pulls closer representations of the same image that has been transformed in some way or the other. Now, this idea you can think of as pulling together similar concepts, so different augmentations of a cat should result in representations that are similar to one another, but it should push away representations for other kinds of categories, like dogs, for example. Now, the hope with training with these self-supervised learning objectives is that these representations become general enough, right? So that when you see something new, maybe a sketch of a cat or a sketch of a dog, it still embeds those in the space so that it's easy to classify exactly what those concepts are. Now, moving on to multimodal, we can take these same ideas, the same objective, and then start thinking about what would happen if we added text to that representation space. So, for example, if we could also embed a representation of the text that says a cute fluffy cat and have that be close to the cat representations, that would be great because now we can sort of query things in both images as well as text. And similarly, if we can also embed the phrase, my favorite dog is a golden retriever, and ideally that representation would lie closer to golden retrievers than other kinds of dogs. So that's the general idea behind sort of adapting the self-supervised learning objectives we've been talking about in class so far to incorporate text and other sort of multimodal inputs. So in SimClear, if you remember, the main objective was that you want to pull together, again, transformations of the same image. So the cat should be closest to its other cat augmentation. So that green arrow right there sort of indicates two things that should be pulled together. And it should be further away from all the other augmentations. So any other image of a dog or a monkey, you want those representations to be far away. Now we can use that same idea and now think about training a clip model. In clip, what they do is they still have that same image encoder that you have on the left-hand side, but on the right-hand side, you now have a text encoder. And this text encoder is embedding descriptions of those individual images. Okay, so your dog image will now hopefully learn that it should be closer to a representation of a text that says, my favorite dog is a golden retriever, and far away from all the other representations. Okay, and because this is the same formulation that you've seen with SimClear, the objective that you use to train a model like this is just by collecting a lot of image-text pairs, and then once you have those pairs, feed them into a model in a mini batch, and then make sure that you have this contrastive objective that we used for SimClear, but now we're applying them across images and text. So we're pulling together here in the numerator the representations of similar things and pulling apart the representations in the denominator for everything else. Now, of course, we want that image to be closest to its corresponding text and far away from all the other text, but we also want the inverse to be true as well. So we have a second objective as well that says every text should be closest to its image and further away from all the other image descriptions, right? So it's a complementary symmetric loss that you have between the two different types of modalities that you're feeding into this learning objective. Okay, so of course, what's really nice about a clip-like model is that it can be trained with just associations of images and text. And there's a ton of this data on the internet. So you have a lot of data of corresponding images and text that you can pull up from the internet, you can download, and now you can train this model at a very, very large scale. And this is exactly what OpenAI did a couple of years ago in 2021 when they released their clip model. So they collected a lot of that data, and then they trained it using this contrastive objective, using all of the images and text pairs that they found from the internet. And then once they were done training that, you follow the same sort of two-step pipeline that you saw in the self-supervised learning class, where in step one, you do that pre-training, and then in step two, you can take that image encoder, and now you can adapt it to a new task. So once you have this pre-trained image encoder, you take its weights, and then you tag on an additional linear layer on top to adapt it to an image classification task or a detection task, or you can put in something like a decoder and even decode out semantic segmentation maps. Right? So a ton of different tasks become possible just by initializing your model from this sort of pre-trained objective. What was really exciting when this paper came out is that linear addition of this one linear classifier on top of this clip encoder led to really large improvements in performance. So here in this graph, I'm showing you average performance across many different image classification data sets, and the clip models, the ones in red, they're all the way at the top. And you can see that as you sort of train on more and more images, you end up getting better and better performance. So it was very exciting because it seemed to indicate that there's this really nice pre-training objective that we've been able to unlock. And there's an abundance of image text data on the internet, which means that we can train these to be very, very large and very, very performant. Of course, that's not the end of the story. What we want to do, ideally, is not to have to adapt these features for something new. We would ideally want to be able to use a clip model out of the box. So in language models, for example, you train a model to autocomplete usually. And this autocompletion kind of works like this. You have a phrase that says, I love, and then your model sort of fills in the next word, for example, cake. And then you train with this pre-training objective. And what you want to do during the second stage is to basically take that same model and adapt it to a new task. For language models, you never have to retrain that model. You never have to retrain it on a new downstream task. Every task is a language task, and so every task can be treated as this sort of autocomplete process. But with CLIP, the problem is there is no autocomplete process, right? So we've trained this model on this contrastive objective, but to adapt it to a new task, we still need training data and we still need a linear layer on top that we need to train to adapt it to new tasks. So a lot of people started thinking about what we can do to sort of adapt this model for, to use it directly out of the box. And there's this clever trick that people came up with. And this clever trick is basically using the text encoder as a way of guiding the model to generalize to any downstream classification task. And it works like this. So let's say you want to classify what this image is using a CLIP model, but you don't want to sort of retrain this model or adapt it for any downstream task. What you can do is you can take the text encoder and pass in a word through that text encoder to create a text vector and use nearest neighbors to figure out what is the right classification. So the way this works is you take all the categories in your new data set. So for example, let's say your new data set contains the categories plain, dog, and bird. You're going to embed all of them in the text space to get a vector for plain, a vector for dog, and a vector for bird. And now when a new image comes in, all you have to do is embed that image using the image encoder and then find the closest neighbor. So in this case, you should find that this image has the highest sort of similarity with the correct class. In this case, it should be the dog vector. And you can see the dog vector does have the highest sort of similarity score. And so because of that, you can now classify that image as a dog. Okay? Now, you can think of this entire process as essentially building a one nearest neighbor algorithm, right? So you have a bunch of centers that or embeddings that you've generated in the text space, and now you can use them as your class category labels, and you're doing one nearest neighbor to find the optimal classification for any new image that comes in. Now, of course, a single word might not be sufficient to get a really good word vector. Instead, what you might want to do is use a phrase. And the reason you might want to do this is because a lot of the internet data, it usually doesn't have words that occur by themselves. CLIP was trained from just phrases that were downloaded from the internet. And so ideally, you want to pick the right phrase that gives you the best representation. So instead of just having the categories plain, dog, and bird, you might instead want to embed a vector that represents a photo of a plane, a photo of a dog. And turns out if you do this one small change, you suddenly get a large boost on ImageNet where you see an improvement of about 1.3%. Of course, picking that right phrase is also something that's very difficult to do. And so what people typically do is they don't just pick a single phrase, they pick many different phrases. So a photo of a dog, a drawing of a dog, or a bunch of different ideas for different phrases. And you want to create many different vectors for all of those different phrases you might think of. And at the end, what you do is you just take the mean vector representation across all of your phrases for each category and use that as your mean dog vector, your mean plane vector, and your mean bird vector, right? And then now you're back to where you started, and you can do your same sort of one nearest neighbor algorithm on this. It probably has been trained on ImageNet. This is, I think, a point to show that you can adapt it to a new task, but I will show you other examples of data sets where it's definitely not been trained on, and it does sort of adapt to that as well. So you get a single vector out. It depends on the architecture you're using. If you're using ResNet, you take the final vector representation. If your text encoder is, let's say, a VIT or a transformer, then you usually take the CLS token of your transformer. Okay, so that's sort of it for CLIP. You could basically adapt this for a wide variety of new image classification tasks. And to your question right now, of course, it's not that big a deal that it performs just as well on ImageNet. But it is still exciting that it does do well on ImageNet at all. What's I think more interesting is that when you look at other datasets that were collected after CLIP came out, so a dataset like ObjectNet, which contains objects that people took photos of in very weird sort of places. So they put a banana on the ground and took a photo of it, or they took a banana that was like really rotten and took a photo of it. So things that are just not common. And so in this dataset, if you train on ImageNet, you don't do very well. Because ImageNet, again, contains most of these categories in its most typical form. But if you take the CLIP model, it performs just as well. And that was really, really exciting for many people, because this ability to generalize to a completely new data set that it hasn't seen before, that's even out of domain to some degree, was really great. So why do you think this is? Why do you think CLIP generalizes a lot better than training on ImageNet? To paraphrase your response, because I think it's the right response, is the text that you download from the internet, it contains a lot more than the category labels. It contains a lot more structural information, contains information about shape, about the colors of things, and all of that adds to the representations. And so these models are able to adapt a lot better to something that maybe is slightly out of distribution, or an object that looks slightly different, because it does have all these other things it's looking for as well. And so that additional supervision really helps quite a lot. The other reason it helps quite a lot is the scale of data. ImageNet is only about 1.3 million images or so, whereas the internet contains millions and billions, at this point, billions of image text pairs that we can download very easily. And so these models have just seen so much more data that this adaptation becomes a lot easier. And so people started doing these experiments on a wide variety of generalization tasks. So they showed that you can generalize these models for not just natural images, but also sketches, that you can also do this on adversarial data sets as well. And performance across the board seemed to indicate that these models are just really, really good and robust to many different applications. And then here I'm showing you the difference between zero shot and linear probe. And you can see that, of course, linear probe, when you add that additional linear classifier and train it and adapt it a little bit, it does improve performance in majority of the data sets, the ones in green. But it's not always the case. In some cases, the CLIP zero shot just performs really well out of the box. And so it just seemed to indicate that we've finally unlocked this capability of being able to adapt image encoders for a wide variety of different downstream tasks. And this is why I think a lot of people talk about CLIP as the first sort of foundation model for images. So let's talk about what makes CLIP work so well. Of course, there's no real labels as such with CLIP. We're just downloading any sort of text associated with images. What makes CLIP work so well is what I was saying. It contained, when it was first trained, it was trained on about somewhere between the parameters were just gigantic. They sort of scaled up the model, and they changed the architecture from ResNet to a VIT. And so you had this transformer architecture with 307 million parameters that was used to train this model. And the second thing that helped was the amount of data, right? So instead of just 1.2 million images from ImageNet, you suddenly had about 400 million image text pairs from the internet that they downloaded and used that to train. So that scale, both in terms of model size as well as the amount of data, helped improve performance quite a lot. So immediately after CLIP came out, people started experimenting with this objective. And there's many different variants of CLIP that have come out over the years, but one in particular that's really stood out came out in 2022. It's called Coca. And Coca took the CLIP model. Here you can see it's the same sort of objective here. You've got the image being encoded on one side, you've got the text being encoded on one side, and then you have that contrastive loss between the two. But they added one additional thing. They added a decoder as well that took the image features from the image encoder, and then they fed it in through cross attention and captioned that image. And turns out this captioning process also helps the model learn quite a lot of rich information. So the general motivation here is that it's not sufficient to just be able to say that this is an image of a cat versus a dog, but to describe that image in text requires a lot more information to be learned by the model. And so the hypothesis is that it's a stronger learning objective, and so because of that, it learns better features. And we found that to be true overall. Coca, when you compare Coca to CLIP, its performance improves quite a lot across all the different ImageNet variants. And overall, there's like a 10% boost in performance across all of the data sets. And I think this was the first time where these sort of foundation models actually beat all the models that we had trained from supervised learning. So at this point, we had many different models that people were putting out onto online leaderboards. And in those leaderboards across the years, you can see the trend sort of going upwards as models are performing better and better. And this is, I think, the turning point where people abandoned supervised learning objectives for image encoders and instead focus solely on just pre-training objectives using these sort of self-supervised learning methods from the internet data. Okay, so let's talk about some advantages of CLIP. CLIP's got a lot of really fun things that you can do with it. It's super easy to train, right? Because it's just a simple contrastive learning objective. It's also really fast in terms of inference. You can embed your entire data set into some representation, and then all you have to do to classify is just do retrieval on that sort of embedded data set. So you can retrieve things very easily with CLIP's representations, which makes it really useful for not just classification tasks, but also search and retrieval tasks as well. Another thing that people really liked about CLIP is that it's open vocabulary. You can feed in any text description and it should be able to retrieve the right images for you. And so that also allows for its applicability across many different domains. And of course, we're going to talk about this later. CLIP is really amenable to being sort of chained with other models. And this idea of chaining started becoming really popular. But hold off on that. We'll talk about that in a few minutes. Of course, I'm telling you all the good things. Turns out there's a lot of bad as well. CLIP, unfortunately, can distinguish between these two images. So you have an image of a mug in grass, and you have some grass in some mug. And CLIP just does not know the difference between these two things. Okay? The reason it doesn't know is because the CLIP's learning objective really depends on its batch size. If your batch size is not large enough, then all of the other batch elements are unlikely to provide any useful supervision for the model. If you're always comparing a cat versus a truck, you're not really going to learn a representation for a cat. Instead, what you get is some sort of representation that's kind of okay at some high level, but if you increase the batch size, you're more likely to encounter other animals that are similar to the cat. And then you learn a much better representation. And then, of course, if you increase your batch size to, let's say, 32,000, and you train it across many, many GPUs, then suddenly you start learning really good representations. You can actually start identifying a Welsh corgi versus another corgi. And this only is possible when you have gigantic batch sizes because it requires you to have other negative examples in your batch that are close enough, that are sort of hard negatives that forces the model to have to learn. Right? So that's very important for getting these models to work well. But unfortunately, regardless of how much people have tried, increasing this batch size doesn't guarantee that the model will learn a good representation for things. And so you're sort of at the mercy of the randomness of your training data. So increasing the batch size does help with some amount of fine-grained concepts, but of course it's still limited. And training on 32,000 amounts of batch size is just too large for most labs to even consider doing. People have identified this error across many different benchmarks and sort of identified that CLIP just doesn't have this notion of compositionality. So this idea that the mug in the grass versus grass in the mug, it's really about composing different concepts like the mug and the grass and the sort of relationship in. All of those individual components are not composed well in your CLIP representations. And there's been a ton of different benchmarks like Winogrand or CREP or ARO. And a lot of these benchmarks have actually come from my lab. They just keep finding over and over again that CLIP has a ton of limitations. And there's a ton of things that they are just unable to do. Now, of course, in reaction, the community immediately started thinking about how do I handcraft my batch so that it contains the hard negatives. You know, so if I have one type of corgi, that I should hopefully have another type of corgi in there, so your model really is forced to learn good representations. And so this idea of training with hard negatives became really popular in the community for a whole 1 year, until we released a follow-up paper that said that if you train with hard negatives, you end up actually unlearning a lot of things about semantics. For whatever reason, and this is something that we still don't theoretically understand, we end up actually with much worse performance in generalization across different sort of environments and different kind of data sets. So there's a lot of work to be done still in terms of figuring out the right way of constructing your data set, the right way of constructing your batches and training signal. So we're still really far away from that. But regardless, people are still very excited about CLIP in general, because it does give you some amount of supervision regardless. Of course, again, image level captions are again not enough. Ideally what we want is more than just that, right? We want to be able to identify not just that there's a person crossing the street, but that the person is in this location, the car is here, the street is here. All of that information, that grounding information, is completely missing in CLIP. And so ideally you'd want also your data set to contain this kind of information and your model to also be able to reason about that kind of information. Also, the final thing that's a big disadvantage for CLIP is that regardless of how big your data set is, even if you collect upwards of, let's say, 5 billion images, it's still not going to be enough to capture all the important things that you might care about. And so there's been a lot of efforts that we've been doing in data filtering. So how do you filter the internet to find the best training data for training these CLIP models? I won't go into that today, but there are all of these sort of mechanisms that people are exploring that's now become the frontier of what today's research looks like in this field. Okay, so that's the first branch of foundation models we talked about. It's about sort of generalizing classification to a whole host of tasks. Now let's talk about vision and language models. So there's a new class of foundation models which has become popular in the last 2.5 years, and we often refer to them as multimodal language models. And I'll start off with this discussion by focusing on Llava, which is arguably one of the first sort of multimodal language models that became very, very popular. The motivation here is that language models which do this next token prediction, this autocomplete process, that process is really useful for adapting to a lot of new tasks. And so can we start thinking about even image models as well doing the same thing? Can we, given an image, also start doing different kinds of reasoning that's similar to this auto-regressive process? And that gave rise to this class of models called vision language models or multimodal models. But of course, this, just to be historically correct, this idea wasn't completely new in 2022. In 2019, Wilbert actually introduced this idea. There's a paper called Wilbert in 2019 that took these image models and language models and put them all together to accomplish a generalization across different tasks. But they were all trained pre-transformers and also mostly use LSTMs instead. And so the rebirth of all of this is what's happening right now with Llava, where a lot of these models switched over to a better architecture, switched over to a better set of objectives, and now aren't just training on individual tasks, but are training on a foundation of a variety of different tasks using some sort of pre-training objective from the internet. So how does this work? How do you sort of think about Llava? So to sort of talk about Llava, let's take a step back and think about the transformer model or self-attention in particular. So when we think about language models, what they're doing is they're attending over the past. So you have a sequence of words that are coming in. So for example, cats are so, and then your model to generate the next word will attend over that historical context and then generate what it thinks the next word should be. So it might think that the phrase should be cats are so cute. And here's another way of sort of representing that same sort of objective. You've got the input text coming in at the bottom, and your model will generate the next word, which is cute. So when we think about vision language models, what people usually are referring to is adding in additional context by grounding that conversation that we're having with some image that we care about. So we might care about tokenizing our image somehow and feeding those tokens into our language model along with the historical context of cats are so, and then using that to autocomplete the rest of the description. So that's the basic idea behind Llama, is sort of feed in these image tokens along with the words that are being generated to continuously generate more words about that image. So of course a question comes in, which is, how do you define these tokens? What should these tokens be in the first place? And Llava, their solution was to use the CLIP image encoder. So they took the CLIP model, they took the image encoder, and then they basically extracted tokens from that encoder. So the first thing you might think about doing is just using the CLS token. So here you've got, let me see if my mouse works here. Oh, it does, okay. So you've got the image coming in over here, and then they're getting patched Each patch turns into a representation that's fed into your transformer architecture in Clip. It goes through a bunch of layers of processing, and then at the end you get a bunch of different tokens for each of the patches, along with a representation for the CLS token. And so far, we've only been considering the CLS token. We've only been doing things with the CLS token for doing any sort of classification task. But there are all of these other tokens in there as well. Now, the problem with these other tokens is that they're never supervised. Right? So the CLS token is supervised with this contrastive objective with text, but the other tokens are never used for any purpose. So they might not actually contain any useful information. And empirically, people have shown that these features are not very useful. But what they have shown is that if you go one more layer back, the penultimate layer in your Clip encoder, these features are actually very useful. So these features are used to generate the final Clip embedding in the final layer, and they contain a lot of spatial information about where objects are in your entire image. And so this is what people typically use when combining Clip encoder with a sort of transformer, sort of LLM based model. Okay, so this is what the entire Llava architecture looks like. You feed an image through your pre-trained Clip encoder. You extract a bunch of features from it. You take those features and you pass it through a linear layer that you need to train. And what this linear layer will train to do is convert your Clip representations into something that the LLM can understand and make sense of. Okay, and once you have these tokens, you now basically pass in all of your tokens to your language model, and it can now generate some conversations about that image itself. So Llava was one of the very first sort of popular models that were out there. And following up, Google quickly released Flamingo. And in Flamingo, it followed very much the entire Llava setup of being able to combine a vision encoder's features with a large language model. But the place where they innovated is how do you do that fusing of these different features? So in Llava, you had the features coming in through a linear layer and fed in as part of the input. In Flamingo, what they did instead was they basically took all the features coming out of your vision encoder and fed them into every layer of your LLM. Okay, so they had to make some changes to the LLM architecture itself, and this is how they made those changes. So here's an example of what Flamingo's training data looks like. You've got images that are encoded, so you've got this dog and you've got this cat. They both get embedded. And they're both going to be fed into every single layer of your LLM. And down here, you've got a data that's sort of describing starts with the image and describes that image. Then the next image describes the next image, and so on and so forth. And they're sort of fed in as input to your LLM. And your output is going to be to autocomplete that last image. Okay, so you got one image followed by a description of the dog, second image, and you start the description, and your model will be trained on auto-completing that description for that second image. So what did they do? What did they change to the model itself? They added this sort of gated cross-attention module to every single layer of your LLM. And they made one other change. They also added this perceiver sampler right here. That basically samples and downsamples your image representations, so there's smaller dimensions and a fixed number of tokens for every single layer. So let me go into some details with what they look like. So this is the full architecture overall. Most of the components are frozen. All the language model weights are frozen. All the vision model parts are frozen. The only parts that are trained are these perceiver sampler components and this cross-attention layer that's sort of added into every single layer of your LLM. So let's talk about what this cross-attention module looks like. This is me zooming into that cross-attention module. So every single LLM layer, right before the LLM layer, you have this cross-attention component. And what its purpose is to look at the image features and then decide what parts of the image features it wants to keep around and what it thinks to be useful for the language model to know about. And they designed it as a set of components that you've already seen so far. So you attend over the image features using a cross-attention layer. And then following that cross-attention, they added this 10H nonlinear activation. And this is basically deciding what parts of these components do I want to keep around, which parts of the image do I want to forget. And then it goes through this fully connected layer where it adapts those representations a little bit. And then again, a tanh nonlinearity to decide again which parts it should keep and which parts it shouldn't. Once it goes through those two components and each one has a residual connection across of it, it then goes to your normal language model processing and then continues to generate the word it needs to. Okay, so these additional layers are being added just as a way for the language to sort of incorporate and attend over the vision features at every single layer. Okay, so the actual modification itself, if you're interested in what this looks like in code, is just about 2 or 3 lines of code where they added this cross-attention layer and then this tanh nonlinearity in between, and that's really about it. So in terms of code, it's a very minimal change, although for the model, it's a very gigantic change because now it can sort of choose what parts of the image to attend to at every single layer of its processing. So you give the model a lot of ability to decide when and how to attend over the vision features. Okay, so Flamingo was very, very exciting, but training it was very difficult. And they had this really ingenious way of training it that allowed our models to adapt to many different tasks. The way they trained it was through this concatenation of a bunch of different images together. So you didn't just have one image and one description. You had a description at the beginning that says, here are some cute pictures of my pets, end of sentence, beginning of image, and then a description of that first image, end of that first component, and then the second image and a description of the second image. Okay? So you had the training set up so that it looks like a long sequence of image, text, interleaved data. And of course, when describing any single image, you don't want the model to look at the entire context. You want it to only look at that one particular image. And so they created a masking scheme where every single image, when generating, only looks at that particular image features and not the other ones. Meaning that when you're generating the description for my puppy is sitting in the grass, you're only looking at the features that correspond to the puppy, only when generating those words. Similarly, when generating the description for the cat, you're only looking at the cat image and not the other image. So there is this sort of distinction where they created this handcraft and masking scheme to make sure your descriptions are always following and looking at only that particular image. But when trained, the model does get to see the entire context of everything that it's generating. So why is that helpful? Why is this entire process helpful of being able to see all of this stuff together? Well, it's helpful because it allows you to do these kinds of applications. So here is 3 different applications that Flamingo was able to showcase. And they all center around having multiple conversations or dealing with multiple images. So in the first case, you've got an image that's fed in. And the Flamingo model describes the image by saying that this is a picture of 2 teddy bears on the moon. And then what it allows people to do is then ask another question. So people can ask, what are they doing? And because it's already being, it's training using an existing large language model, that large language model's reasoning capabilities are inherited, and now it can reason and answer this particular question. It can now answer and say the teddy bears are having a conversation, and then a user might ask, what objects are they using? And again, Flamingo can say that it looks like it's a computer, and so on and so forth. So you can enable this multi-turn dialogue about an image simply by doing 2 things. You train by first pre-training the language model and then incorporating that language model into Flamingo. And secondly, allowing your model to see many different images and many different turns throughout its training data so it can adapt to longer sequences of text. You can also give it multiple images and ask what is a common thing about these images. And now the Flamingo model will look at each of those different components and sort of reason and say that they're all flamingos. So you can start doing a lot of these kinds of really cool applications. People also showed that you can start doing in-context learning. I don't know if this is something you've seen already with language models, but I'm sure you've used in-context learning with GPT, where you tell GPT, here's an example of what I want, give me more things like this. And you can do the same thing with Flamingo, where you can pass in an image and a description, an image and a description, and now when you pass in a new image, it'll give you a description. Or you can say, here's some image, here's a question and answer, here's an image, question and answer. And then when you pass in a new image and just ask the question, it'll give you the answer. Right? So you're not training it to do these different kinds of tasks, but you're providing it with examples of behaviors that it should have, and it should just generalize to new kinds of behaviors that you might care about. Similarly, you might care about just classification, and you can use Flamingo to do classification as well. So you can give it an image and say, this is underground, this is Congress, and then you can ask, what is this, right? And you can also even teach it to do OCR and math, where you give it an image and say, oh, this should correspond to 2 + 1 = 3. And so eventually when you give it a new image, it should be able to autocomplete and extract out 3 times 6, and then also give you the output by reasoning through this entire process. Yeah, so this would be an example of few-shot learning, where you give it some examples, a few examples of things, and then you ask it what the new thing should be. If I were to throw away all the in-context examples, that would be zero-shot learning. So we're not concatenating them. We're technically passing the image tokens through this perceiver sampler into every single layer of your LLM instead. And so only the text is ever concatenated and fed as input to your Flamingo model, and it chooses when to attend to which parts of the image. You give it to it once, but behind the scenes, of course, this is the interface, right, the web interface. But behind the scenes, what they actually do is they cache the model, assuming that the user will want to continue talking. And so the model is cached and ready to accept more tokens. Yeah, but if they did not cache it, then yes, it would pass in this entire conversation as input. Yeah. Okay, so Flamingo is super cool because they have these really big tables in their paper that you can go check out. But what was really cool about it is there were all of these tasks that were very difficult, and you had to adapt Clip to do them. But Flamingo was just able to do it with zero-shot or few-shot, and you start seeing these gigantic improvements across many different benchmarks. And this is when I think the field shifted from reporting on a few classification benchmarks to reporting on any sort of understanding task at all. As long as you can frame it as a question-answering process, you can build benchmarks for a wide variety of skills. And we started seeing that become the norm in the last 2 years in the computer vision field. Okay, so this is where we were, I think, sometime last year. And seeing the success of Llava, a lot of companies started investing quite heavily on these models. And so you started seeing a lot of API models like GPT-4o, GPT-4v, Gemini 1.5 Pro, Gemini 1.5 Flash. A lot of these models started being released. And even Anthropic came into the picture with Claude 3 Opus. And now, of course, Claude 4 Opus is out. And so you had a lot of these models come out, and they were performing a lot better on a bunch of these benchmarks. So here I'm showing you the average performance across 11 of the more popular visual understanding benchmarks in the field. And there's this gigantic difference, right? So the difference between Llava, the model we talked about, that's open source, that's down here at about 43% accuracy on average. Meanwhile, GPT and all of these other models are performing much, much better at about somewhere like 80s or high 70s, right? So big difference in performance between these two different kinds of models. Of course, immediately seeing this sort of difference, people started distilling GPT and Gemini into distilled variants and trying to release those models. So Alibaba, which is a company in China, they released this model called Qwen. And then there's Intern VL, there's Phi, there's all of these different models that started coming out. And all of them were distilled from GPT, and if not GPT, then Gemini. Now, that led to a big problem in the field. A problem that's become a big part of what my own research agenda has been trying to sort of focus on, which is we don't actually know as a research community how to build really performant vision language models. The tricks behind how to build them, only the people in OpenAI and Gemini in Google, those teams know how to build these kinds of models. But the open source community, they're down here. They're down here. This is where the research community was as of last year. Of course, you can argue these are really nice open models, but they're not really open. Because they're distilled, we don't actually know how to reproduce these models, right? We can only produce them if GPT exists. But if GPT doesn't exist, we don't know how to create these other models. And so what my own research agenda has been focused on over the last couple of years is figuring out how do you close this gap? How do you build really good multimodal language models and disseminate that sort of understanding to the entire community? And so what we've done over the last 6 months or about a year now is we've created our own sort of class of models that we called Molmo. And I'm showing you Molmo's performance up at the top. And what sort of sets Molmo apart from all the other models out there is that it's completely open source, meaning it's open weights. So you can download the model. It's open data, meaning you can download the training set as well as the evaluation set. It's also open code, meaning you can basically train your own Molmo in your own home, assuming you have enough GPUs. And you can also evaluate, add on new evaluations, adapt this model for all kinds of new things, and of course, start using it for a wide variety of different contexts. Now, of course, academic benchmarks are not enough, right? Because what we care about at the end of the day is, are people going to use these models? Will people want to use these models over GPT? And so to make sure we had that evaluation properly done, we released a playground with a Molmo, and we did a gigantic user study where we actually compared head-to-head outputs from our models versus outputs from all the other models. And our model has the same ELO rating as GPT. It comes in second with a difference of 1 in ELO rating versus GPT-4o. This is that same graph rotated so that I can show you some examples. This was a gigantic evaluation, by the way. This was about 870 users that we showed these model outputs to, and we did about 325,000 pairwise comparisons. We asked people, which model's output do you prefer? Our model, the Molmo model, ranked, again, like I said, second, more or less a coin flip between what people preferred between GPT and our model. But it already beat out Gemini 1.5 Pro and Claude 3.5. Now, the big difference is we are a small research lab, and we're beating out Google's billions of dollars of investment into Gemini, as well as Anthropic's billions of dollars of investment, and already matching GPT. And so we were quite excited by this entire process. But we also developed a 7 billion model that comes in right after those big models. And that 7 billion model is really exciting because you can put it on a single GPU. So you can now have this model capable of doing a wide variety of vision tasks that works on a single GPU, meaning a lot of people can now use it and fine-tune it for all kinds of things. We released this model in September 25, and the community was very excited by it. This is the first time a very performant multimodal vision language model was released, and a ton of people started talking and writing articles about all the ways they want to use it. One of the use cases that kept popping up over and over again was this idea of using Molmo finally for robotics applications. And I won't talk about robotics today because you're going to learn about it in the next class. But I do want to give you some examples of things that people were excited about with robotics. But a ton of people, even like folks at NVIDIA, started chatting about how this is, you should never bet against open source. Regardless of how much model development you do in private, eventually the open source community will catch up, and we were catching up at that point. And so seeing our model out, Meta quickly released in response their Llama 3.2 model, and a lot of people did evaluations comparing Molmo versus Meta's Llama model. And again, I'm very happy that we came up on top of Llama as well. So let me show you why Molmo does so well. What was the sort of trick to getting these models to work very well? The trick was to ground its decision-making in the pixels itself. So usually when you give a model a question, like count how many boats there are, it'll give you some number, and oftentimes it hallucinates. But what sort of sets our model apart is that it actually points to all the things that it's counting. So it generates points to all the boats, and then it outputs a final number. So its decision-making is grounded in the pixels itself. And this allowed us to essentially train a model that, unlike Llama from Meta that was trained on about 6 billion image text pairs, our model was trained on only 700,000 image text pairs. The big difference was that we hand curated this 700,000 image text pairs. And that was the biggest sort of difference between what we were able to do versus what these models that these companies were building were doing. So a lot of folks are trying to currently download these image text pairs from the internet, right? That's been the foundation of how a lot of people train these vision language models. You collect a lot of internet data of images with their associated text, but the problem with internet data is that it's incidental. The text that's often associated with an image describes something subjective or something that the uploader felt about the image. It rarely actually talks about the contents of the image itself. And meanwhile, this is what our data looks like. right? So for a single image, we have a dense description of the actual contents of that image. And we have things that people never talk about on the internet. There's a ton of tacit knowledge about the visual world that we just never speak about. I will never tell you that something is to the left of something else, just because it's unnatural for us to do that. It's just so obvious that something is to the left of something. Why would you ever communicate that information? So that's the kind of information we started eliciting from people. We started getting people to talk about how things have particular size, like large, or its shape, like rectangular. We talked about its material, like polished and rich, and its positioning across the image, like it spans the horizontal sort of plane of the image. So all of this information really is what makes these models more performant. Here's another example from the data set. Here's a very simple image of a phone screen or a tablet screen. And we have information here that, again, is completely missing from the internet. Things that people would find helpful. Things like, this is a tablet device. The time is this. The amount of power left in your device is this. This is the kind of information that would help people use these models. But this is, again, the kind of information we never talk about on the internet. And so to get this kind of information, we designed a lot of different questions. We spent 2 years doing different kinds of elicitation studies to figure out what are the right things or pieces of information that are missing from the internet, and how do we elicit them as effectively as possible. One thing that was very important is we had all of our annotators not type descriptions, but talk about descriptions. Talking automatically breaks a lot of stereotypes around Gricean maxims. And so by getting people to talk, we got them to speak about things that they would never usually type. The model itself didn't look any different from Llava. We had the same sort of setup of a clip encoding coming in. You had a connector that was just a linear layer. And then you had a large language model that would take in all of these tokens and then output any sort of thing that you care about. So the model itself looked very similar to existing models. The biggest difference was in the data and the quality and density of the data itself. And because of this sort of grounding capability, where the model grounds its decision-making in the image itself, you could get Molmo to do things that you can't use any of the other models to do. Things like point to the menu. It actually tells you where that menu item is. Or you can tell it to sort of point to where I can set my search options, and it'll show you, okay, this is where you might want to set those options. Or point to where the mid-size data sets are, and it'll tell you what option you need to move. And I already showed you that you can point to count, but you can also point to do really fine-grained things, like being able to sort of ask, what is the route number on this bus? Molmo doesn't just simply give you an answer, it actually points to where in the image. In this case, there's this area right here that contains the bus number, and then returns the bus number to you. You can ask it to reason about how many cars on the left versus how many cars are on the right. You can ask it to reason over depth images or overhead images, or even really crowded scenes and sports areas. What's also really exciting, and again, we'll talk about this in a few minutes, is this idea of chaining that keeps coming up all across multimodal models today. The idea of chaining Molmo to other models. What you can do is chain the output of Molmo to become the input of another model like SAM2. And so you can tell Molmo to point to the cricket bat. And now you take that point, you feed it to a model like SAM2, which does segmentation. And now you can do segmentation of that cricket bat across time. And so you can start enabling all kinds of new applications. Here's one that we played around with in the office, which again, you're going to hopefully learn about in the next lecture when you hear about robotics. But we asked Molmo to point to where the water bottle is, and then we moved the robot using simple motion planners to that water bottle. Next, we ask it to go move that water bottle to where the dirty dishes are. It points to the sink, and then moves the robot there. And then we tell it to go point to where the free space is in the sink and put that bottle in that location. So again, you can sort of combine all these capabilities together now and chain them to even sort of automate a lot of robotics applications. This has been a lot of focus in my group now, is sort of adapting a lot of these vision language models and enabling a lot of generalization in the actual physical domain. So the question is around, would these models be able to sort of point if we're always sort of changing the resolution of the image to be a fixed resolution, right? Well, turns out that you can actually adapt these models to be any resolution nowadays. There are these mechanisms like FlexVIT that has introduced a way of allowing for any variable size image input, and you can adapt them to sort of point in that new space instead. So your model's position embeddings basically change depending on how big your image size is, and your models, you typically tend to generalize well. So that was sort of the conversation around adding vision and multimodal models together. In the last sort of 20 minutes that we have left, I want to talk about generalizing these foundation models to not just deal with image classification and text, but be able to sort of generalize to any sort of output space you might care about. And one of those models that's become really popular in this space is this segment anything model. The segment anything model, or SAM for short, what it tries to do is it tries to build a segmentation model that's a foundation model for all kinds of segmentation tasks. So really what they're trying to do is allow anybody to sort of point to things that they care about in the image, and then hopefully have that thing be something that the model can sort of output a mask for. So for example, you want a model that generalizes beyond just a fixed number of categories to any sort of category you might care about. And you would ideally want these outputs to be masks for any sort of category that is of interest to the user, right? So those are the two goals, that we want to generalize to any category, a huge number of categories. And we ideally want to be able to very specifically output something that the user really cares about. So they're both challenges. They're both challenges in figuring out how do you collect a large amount of data that spans a wide variety of categories, as well as how do you design an architecture that really pinpoints what the user really cares about. Now, let's start with the second question first. It's really ambiguous when we want a mask for something. So imagine a scenario where you have two cats in an image, and a user comes in and says, hey, I want a segmentation for the cat, but it's really not clear which cat they want a segmentation for. Ideally, again, if you had Molmo's pointing capability, you could actually point to which cat you care about, and then depending on the point, you could create the masks that matter. Now, of course, these are not very good masks, and ideally you want these masks to be very, very good at quality that can sort of support a wide variety of downstream applications, like image editing or any kinds of other things you might think of. So to build this architecture that allows any user to be able to specify exactly what they care about, we needed to go beyond just simply typing in text what you care about, right? So what the SAM architecture has is two components, or three specifically. It's got the image encoder, which is, again, it could be a clip encoder. And it's got a prompt encoder, which is something special. This prompt encoder really tries to encode text or points or bounding boxes or any way that a user might want to specify what they care about. And then given these two things, it passes it through this really lightweight decoder that outputs a mask. And the decoder looks very similar to like the segmentation decoders that you've already seen in this course. So overall, this is what the model looks like. Given an image, we encode that image using an image encoder. And then you have a bunch of different prompts that are going through and interacting with these image encoding through a decoder, and you output a mask, right? So this is the overall architecture design. Now, there's one big thing that is a problem with segmentation. So let's say a user does point at this particular location and says, hey, I want a segmentation mask for this location. Now, the problem with that segmentation mask is that it's still ambiguous. Even with a point, it's still not sufficient, because that point might be referring to the entire scissor. It might only be looking and referring to the parts that you can hold, or it can be referring to one of the parts that you can hold. So this ambiguity is really difficult to sort of resolve for. And you don't want to penalize the model for picking the wrong one. So what the SAM architecture does is, instead of outputting one segmentation mask, it actually outputs 3 segmentation masks at different levels of granularity. And then it picks the one that is the closest matching to ground truth, and then uses that to calculate the loss, and therefore not penalizing the other ones. So the hope is that overall, over time, this model will learn to output all different kinds of masks, and then the user gets to choose basically which one is the most appropriate for their use cases. Okay? And if you put all of this together, the only thing you need now is data. You need a lot of data across many different categories to really make this model possible. Now, the problem with data is that until this model came out in 2023, this was about a year and a half, maybe 2 years ago, when this model came out, most of the segmentation data sets were extremely small. And what the authors of this paper did is that they grew the amount of segmentation data sets that were out there, the amount of images, by about 6x, and the number of segmentation masks by about 400x. So they significantly grew and collected a lot of masks to make this model as performant as possible. So again, the message is very similar to the message we had with Flamingo, the message we had with Molmo, and the message is you read really good high quality data to really get these models to be as performant as possible. And for a lot of vision tasks, the data is completely missing from the internet, and you need to go out and find and collect that data to get these models to work very well. Okay, and so to make this data happen, they created this sort of in-the-loop process where they initially had some amount of data annotated. From that annotation, they created a training data set, they trained a model, and they used that model to annotate more data, and then they iteratively refined that model-generated segments using users and continued this process. So they had this human in the loop, model in the loop process of proposing segments and then fixing the segments using human annotators. This is what an example image looks like from their data set. You have quite a lot of categories. Each individual vegetable here is annotated with its own mask. So they're quite expensive to collect. And they did this across a lot of images, millions of images. Here's another example where, again, all the single umbrellas are annotated. Again, here's another one with underwater sea. And of course, paintings as well. They have segmentations of paintings. And so all of this together is really what was foundational to making this foundation model for segmentation. Okay? So that's for segment anything. And I want to use the last couple of minutes that I have left today to really focus on chaining, which is the last part of multimodal language models. The idea behind chaining is something you've already seen. I've given you hints already throughout this lecture. And the idea is to be able to combine different models together to enable things that a single model can't do alone. Here's a fun little exercise we can do as a class. So I'm giving you 4 images, and I'm also giving you 4 categories, right? And these are potentially categories that some of you have never seen before. And they're also categories that Clip hasn't seen. And so Clip actually fails at these categories because it doesn't have any idea which one's associated with what. Does anyone here know which one is what? Marimba. Yeah, the second one is a marimba. That's right. Yeah. There's one that's a little easy, the viaduct. Right? Yeah, I think a lot of you know which one that is. But yeah, which one's the dog and which one's the bird? What if I gave you these instead? So now I'm giving you descriptions of these things. And it suddenly becomes very easy for you to associate each one with the right category, right? And that's the basic idea behind chaining. That even if Clip has never seen these images, chances are these concepts have been talked about on the internet to some degree. And it's likely that GPT might be able to describe it. And if GPT can create those descriptions, now those descriptions become really good ways of classifying exactly which category is which one. And that's the idea behind chaining, is that you take the strengths of one model and you combine it with the capabilities of another, and suddenly you get all kinds of new capabilities that you didn't have before. And so you can take a ton of categories that have no training data in Clip, but if you can describe all of them, because Clip has seen a lot of descriptions for things, it can now start classifying all of them very well. And you can start getting Clip to generate classifications for individual flowers or individual cars or individual spaces or even different kinds of pets. And you start seeing these improvements on a bunch of different data sets that are about more fine-grained, specialized categories. And the only way it's able to do that is because GPT has ingested some ability to sort of describe those things. And this idea of being able to generalize the new capabilities is something that was extremely popular last year, and it still remains very popular this year. And it's through this idea of chaining for any sort of question at all. So for example, if I asked you, are there 3 people in the boat? The way you might want to do this is by, again, asking a multimodal language model to answer this question. Or what you could do is use all of the hundreds of specialized vision models that we've been developing over the last few decades. So there are object detection models that you learned about in class. If you use an object detector, you'd be able to get a detection for each of the 3 people, and then you could just say, oh, they're 3 people because they're 3 detections, right? So that's a general idea, is you can chain other models' outputs together so that you can do new kinds of capabilities. Here's another example. If I asked you how many total people there are across these 2 boats, is it 6? And again, you can do the same thing. You can write a program that does object detection on image 1, and then object detection on image 2, and then adds up all of those components together. right? So this is the basic idea behind what we now call chaining, and this was popularized by a paper that won the Best Paper Award last year called VisProg. And in this VisProg paper, the visual programming paper, the idea was that you take any image or any sort of question and you generate a program. You generate a program that says, answer something about image 1, answer something about image 2, and then combine those answers together to give you the final answer. Right? So you write a function in Python, and then in that Python function, you have individual calls to other models that we've already seen in training. Right? So for example, when asking this particular question, deciding if this statement is true or not, the left and right image contains a total of 6 people and 2 boats, you can ask GPT to actually create a program that tries to answer this question. And then you can take the answer from its program. Okay. And you can also get GPT to do in-context examples where you give it examples of programs that it can generate using other functions. And we can see that it generalizes to new sort of questions and you start using all of the functionality that it has available. Of course, the one thing you need to do is give it the functions themselves. So you need to tell it that, hey, you have these capabilities from other models that you can use. You can localize things using an object detector. You can localize faces using a face detector. And you can have all of these different capabilities across many different sort of other models that people have created, and you could chain them together to do different kinds of tasks. Yeah, so there's 2 different ways of doing it. One is a static way of doing it, where you want to give it as diverse examples as possible and then hopes that it generalizes. Another one is to dynamically choose, given this question, what are the best in-context examples I should use? And so you can treat that as another retrieval process where you retrieve the best examples and then you ask it to generate a program. And that tends to perform a lot better, but only if you have a good retrieval system. Yes, it would require a lot of compute. So there's compute in terms of calling GPT, which you have to do through an API, and then you have to load each of these individual models into your memory and then run each of them sequentially. So it could actually be a lot more costly. And so what people are trying to do is figure out, can we distill these capabilities into a single model? And that's a big part of what research looks like today in 2025. But of course, people are also still trying to figure out how do you chain these things effectively very well. Yeah, you can think of it as like an agent. Yeah. So you have an agent that's basically deciding, hey, given this question, what are the other models I need help from? And how do I sort of stitch them together to do new kinds of capabilities? So that's what it looks like. Yeah. Here's another example where you might want to do image editing. You might care about replacing the desert with lush green grass. Of course, image editing models are still in its infancy. And so what you might want to do instead is call a segmentation model, identify the desert, and then only replace the desert parts, those pixels, with grass. And then you can sort of composite them together to make a new image. Okay, that's sort of all of the things I wanted to talk about in terms of different capabilities. So you've got here are some capabilities around how to think about foundation models. It really is, at the end of the day, an ability to sort of train a model for a single task, and then from that single sort of task, generalize to many different downstream applications. And we talked about in classification how you can create these models by just taking a lot of image text pairs from the internet, training them together to do different kinds of tasks. And that allows you to generalize to new kinds of data sets that might not even exist in the real world or have any labels for in the real world. You can also combine them with language models and train them to do in-context examples like captioning or counting or OCR. And these are, again, capabilities that enable many different applications. And then, of course, the outputs don't always have to be language or categories. They can also be segmentation masks, where you can take different kinds of masks depending on different user inputs. And you can generalize this even further by combining many of these foundation models or even smaller models together through programs and do all kinds of new things. So hallucinations still happen all across the board. What we're showing is that it seems like pointing does sort of reduce hallucinations quite a bit, because it does need to find some evidence for its generations. But that being said, there's no guarantee that it's going to point to the right thing at all. So there's many different ways of sort of fixing for this. One is, of course, collecting more data related to the kinds of reasoning that you want it to do. But a better one is to even have verification methods that verify based on the points whether the output is something you should trust or not. So a lot of the bigger models and bigger companies, what they typically do when you use any of their models is they don't have a single model that's generating an output. You usually take that output and pass it through other sort of verifiers before it even gets to the user. And that mitigates some of these sort of problems. But it is an active line of inquiry right now. How do you sort of reduce hallucinations and also improve these models' actual accuracy? Yeah, so repeating your question, is it possible for these models to build new tools when a capability requires a tool that it doesn't have? Yes, it can. We have a few sort of preliminary experiments in those directions as well, where you can tell a model, here's a capability that I want, and what you can build is a system that automatically tries to collect training data and builds a tool for specific use cases. But that line of work is still, again, in its infancy. It's one that we're actively working on, but a lot of folks are excited about that direction.